In model predictive control, the key component is the cost function. It allows you to prioritize your actions. In this particular case, you have two terms, the error and the control action term. Notice the Q and R matrices here. They are called MPC weights, and they act as penalizing variables. They allow you to communicate to the MPC algorithm whether it's a bigger priority to reduce errors or control actions. Higher values in the Q compared to the R matrix means that you're allowing your control actions to act with more freedom in order to drive the error to zero faster. You are penalizing large errors more. Conversely, higher values in R compared to Q means that you penalize high control actions more. You are essentially saying that it is more important to be conservative with control input actions, even though that means driving errors to zero slower. Reducing errors fast is less important than keeping control actions low. That could be the case where you have very little resources in terms of energy or actuator capabilities. If we now look only at the error term, then you have three different errors: roll, pitch, and yaw, or phi, theta, and psi respectively. You can apply the same logic to the weights here. Say that it's more important to you to reduce pitch and roll compared to yaw errors. In the diagonal Q matrix, you apply larger numbers in Q11 and Q22 and the lower one in Q33. If you write out the matrix vector form, you will have three quadratic terms. E phi squared and E theta squared will be minimized more forcefully compared to the E psi squared. What if I decide to put weights in the off-diagonal elements in the Q matrix in Q12 and Q21? Could it be beneficial? I recently created a Linux-based real-time control systems testing environment for autonomous UAVs, and it can show us what happens when you have non-zero non-diagonal weights. Every time I run the simulation, the UAV either tilts diagonally more and more in one or in another direction. Why is that? What causes it? The reason is quite straightforward. Remember when I said that large weights minimize the error squared terms faster? Since you have a variable squared, the lowest number you can have is 0. However, if I write out the vector matrix form with non-diagonal weight matrix elements, we will also have terms with roll error times the pitch error. This term can be negative because one error can be positive and the other one can be negative. Since stronger weights minimize terms more forcefully, the MPC algorithm will produce inputs that will make the term more negative. This term becomes more negative when one error becomes more positive and the other one more negative. Therefore, by assigning larger off-diagonal weights, you are not minimizing the errors. You are minimizing their products, which means that you are increasing their difference. You are making one error more positive and the other one more negative. And that is exactly what you see in the UAV simulation. Following the right-hand rule convention, you can clearly see that the roll error about the blue axis becomes more negative and the pitch error about the red axis becomes more positive. Conversely, if the UAV goes diagonally in the other way, the error about the blue axis becomes more positive and the error about the red axis becomes more negative. There is no way it can be beneficial for controlling a UAV. Therefore, you should simply keep non-diagonal elements 0 and only insert positive values in diagonal elements.